Good afternoon, guys. We are meeting once again. Power Machines N6. Our topic for today is steam turbines. So we are given the following: two wheels of a velocity compounded impulse. A turbine have a mean blade speed of 150 meters per second. The nozzle angle is given as 25, and the steam leaves the nozzles with a velocity of 800 meters per second. The exit angles of the first moving row are fixed, and second moving row of the blades are 25 degrees, 27, 30 degrees respectively. There is a loss of 10% in velocity in all blades due to friction. Determine using a scale of 1 centimeter equals to 50 meters per second. So we are supposed to determine the inlet angles of the first and the second moving rows of the blades, the power output of the two wheels per kilogram per second, and then the diagram efficiency. So first and foremost, what we need to do is to determine our U. So our U was given as, you can come here, our U is given as 150 meters per second. So we divide it by our given scale. Our scale is 1 centimeter equals to 50 meters per second. So we divide by 50 meters per second. In other words, we have 3 centimeters. So from there, now that we have our U, which is 3 centimeters, in the exam, you are going to be using the landscape format. But in this case, because I'm using a wider page, I can draw anyhow. But you must always remember, when you are measuring a U, position your U closer to your left side, because remember, the inlet lines on your turbine are always the longest, and the lines on your left are the shortest. In other words, the inlet lines on your impulse turbine are the longest, but the exit lines on your turbine are the shortest if it is an impulse turbine. But if it's a reaction turbine, please position your U or your blade speed or our B at the middle of the page. Now we can start off together here. We have our U, which is our blade speed, which is given to be 3 centimeters. So I can come to a point like this. I measure my 3 centimeters. This is where my 3 centimeters is ending. So I can just mark here the points. So U equals to 3 centimeters. So maybe before we waste time, I can go down and then do the same thing for the second stage. Remember, our U for the first stage and the second stage, they are equal. Okay, maybe up to a point like this. I mark my U once again. U equals to 3 centimeters. So I have my U, which is already drawn to scale. Now let's go to the second part. The question says the nozzle angle is 25 degrees. So you hold your protractor at this point, because this line is our nozzle area. So you come to this point. You make sure you put your protractor in a straight way and you hold it nicely. So you come to a point where 25 is. So this is 20, this is our 25 degrees. So you take your ruler, you draw a line at that point that you have marked. So you can draw a line. In the exam, I know you'll be using a pencil, but since I'm using a pen, I will try to make my lines short. So our U, we are getting, rather our alpha, we are getting it as 25 degrees. So this angle is 25 degrees. While we are on the same stage, they are telling us that our nozzle velocity is 800 meters per second. So nozzle velocity, that's our V1. So V1 equals to 800 meters per second. We divide it by our scale, which is 50 meters per second. So what do we get there? It's 800 divided by 50. So I'm getting 16 centimeters. So at the far corner of a nozzle angle, you take your ruler, you measure a distance of 16 centimeters. So you measure a distance of 16 centimeters. At this point, that's where your V1 is ending. So V1 equals to 16 centimeters, which is 800 meters per second. Where your V1 line is ending, you don't need to look for this other line. What you just do, because we already know where one of our inlet lines is ending, so you can also draw a line that joins to this part. That this line becomes our VR1, or our relative inlet velocity. So we can measure it to see how many centimeters does it measure. I'm getting 13.4 centimeters. So VR1 equals to 13.4 centimeters. So you can see we are done on the first part. Maybe before we go there, we can take our protractor. We measure our angle of the relative inlet side. So you put your protractor in a straight line where it is cutting on this line. So yes, cutting at 30 degrees. So I'm getting 30 degrees. So I can just put some dotted lines here, so that when you are measuring our inlet flow velocities, it becomes easier. Okay, up to a point like this. Here you can make sure that you have a straight line, or you have something like 90 degrees. You can also draw some broken lines here, or some dotted lines. From this point to this point, we have our VFI, which is our inlet flow velocity. So we can measure it. How many centimeters does it measure? I see it measures 6.5 centimeters. So it measures 6.5 centimeters. So we are going well there. I hope you have seen what is happening there. The second stage which we can do, because already we have measured our inlet flow velocity, we can now go to the second part and check what are we given on the second part. They are telling us that from this point, the exit angles of the first moving row. So our first moving row, you must not forget our first moving row. This is our first moving row, because already we have this outlet. So we need our first moving row. Our first moving row, the angle is given to be 25. The exit angles of the first moving row, so you come here, you highlight, this is 25. So at this point, you once again take your protractor, you mark an exit angle of 25. Where 25 is ending, this is our 20. So our 25 is at a point like this. So you mark it. After marking that point, you draw a line that cuts at that point which you have marked. So you draw a line that cuts at this point. This angle, we got it as 25 degrees. That's our beta exit. So our angle is 25 degrees. So if it's 25 degrees, what we can do now, we can finish up the upper part because we know revision for N5, we have this formula, VR2 equals to VR1 times our K. So we are looking for this line, which is our VR2. So to get it, already we have our VR inlet, which is VR1, which we said is 13.4 centimeters times our K. Our K, that's our loss due to a friction. So we need to get our velocity coefficient of friction. Since here we are given our K becomes 100 minus the loss. The loss was said to be 10%, so we are getting 90%. So if we divide it by 100, our K becomes 0.9. So our K becomes 0.9, so you come here times 0.9. So let's get our relative exit velocity for the first stage. So it's 13.5, rather 13.4 times 0.9. I'm getting 12.06 centimeters. So in essence, we are just going to measure 12 centimeters. So at the corner here, where our exit angle is marked, at this point, we now measure 12 centimeters. So let's measure and see where our 12 centimeters is going to take us up to. So it comes here. Make sure that your line is straight. Yes, up to a point like this. So our VR2 equals to 12 centimeters. So where it is ending, here we don't need to know the other line for this one. You just take your protractor, you make sure that these two, they intersect at this point. So you can draw. Okay, you can draw your line. Perfect. So after that, we can now measure our line. Where this line, how many centimeters does it measure? I see it measures something like 5, 6, 7. Let me check once again. So it measures something like 8.3. So we have V2 equals to 8.3 centimeters. So you can see now that our upper part is almost complete. So we can also look for this angle here. Let's look at this angle where it is cutting on our diagram. You put your protractor in a straight line. So we check where it is cutting. I see here it's on 30. Yeah. So here I'm getting an angle of 30 degrees. So from there, you can put your broken lines so that it becomes easier for us to measure the exit flow velocity. So here, make sure that you put a straight line, then you put once again your broken lines. So let us measure the distance from here to this point. I'm getting 4.5, 6, 7, 8. So I'm getting 4. VF2 equals to 4.8 centimeters. Don't forget, VF2 is same thing as VF exit. In other words, that's our exit flow velocity. And this is our VF inlet, our inlet flow velocity. So I'm really happy. If you check, our upper part is done. So what is left is for us to wrap up on the second part of our turbine. Now, on the second part of our turbine, we are still here. The exit angles of the first moving row, we said it was what? 25, which we are done with. And then 27. The exit angles of the first moving row, and then fixed. So our diagram here on a two-stage, it is fixed at this point. So our fixed is what? 27. I'll emphasize these two angles and this one. when the diagram is complete. So our first angle is said to be 27 degrees, 27 degrees. So you put your protractor here at a point like this, make sure it's straight. So you mark an angle of 27, 25, 26, 27. So it's at a point like this. And then you draw a line that cuts at that point of 27. So I have 27 degrees. So fixed is said to be 27, and second moving row, which is what, 30 degrees. So second moving row, which is 30 degrees, we come to this point. You also measure an angle of 30 degrees. That's our second moving row for the second stage. So we draw a line once again, and that cuts at this point. So this angle is said to be 30 degrees. So once our diagram is like this, we can simply say the diagram is dead. So our diagram in this case is fine. We have our line, this line becomes 2V1. So we have a formula which we can use, which says 2V1 equals 2V2 times our K. So we are now trying to use our first stage diagram to interpret the second one. Our 2V1 is what we are looking for. So if you check here, our V2, we already looked for it here, which we got as 8.3 centimeters. Our K is 0.9. So let's punch and see what are we getting there. 8.3 times 0.9. I'm getting 7.5. So we have 7.5 centimeters as our 2V1. These two, we are just using it to emphasize that we are dealing with the second stage. So we measure 7.5. So if you come to this point, that's our 2V1. 2V1. This is 7, so 7.5. It's at a point like this one. So this way, our 2V1 is ending 7.5. That's our 2V1. So from there, we just take a ruler, you join this line. This line, it's our 2VR1. In other words, it's our relative inlet velocity for the second stage, or it's our moving a blade, but for the second stage. So these two, it symbolizes or denotes the second stage. So let us measure and see. It's measuring 4.6. So it's 4.6 centimeters. And then, now that we have our 2VR1, we can now use the formula 2VR2 equals to 2VR1 times our K. Yeah, so don't forget, these two, we are just using it to symbolize that we are dealing with a second stage. So do not use it in your calculations. Okay, so our 2VR1, we got it as what? 4.6. Our K is 0.9. So let us substitute and see what are we getting. 4.6 times 0.9. I'm getting 4.14 centimeters. So our line 2VR2 or VR2 for the second stage, you come from this point, you measure, it's 4.14 centimeters, which cuts at a point like this one. This is where your diagram cuts at a point like this. So you measure, we have measured already, which is 2VR2 equals to 4.14 4 centimeters. So the few things that are remaining is to get our flow velocities for the second stage, as well as the angles. Yeah, we also need the angles. So we do like this, we put our broken lines. So here we come, put once again some broken lines. Let's see what are we getting here. I'm getting my 2VF inlet is 4 centimeters. And then we come here to our discharge. Let's come to our discharge. We check, it measures how many. So make sure it's a straight line. So I'm getting 2.5 centimeters. So our 2VF exit, I'm getting 2.4 centimeters. So our diagram is complete. What is only left is to get this angle and then this angle. Once we have done that, our diagram is complete. So let's put our protractor and see what are we getting. So here I'm getting 43 degrees. Let me go to this other side and see what am I getting. Must check closely where it is cutting. So here I'm getting something like, let me check properly. Yeah, something like 70 degrees. So our diagram is done. So what we now need to do is to measure the wheel velocities of the two stages. So we need to get our wheel velocity, so which you measure from the two ends of your inlet and your outlet velocities. So let's check what are we getting there. I'm seeing this is 22.5. So W1, I'm getting 22.5 centimeters. Let me measure our W2, or the wheel velocity for the second stage. I'm getting something like 7 centimeters. So W2 equals to 7 centimeters. So that's how our diagram must look like. That's how our diagram is supposed to look like. So we are done when it comes to our diagram. The only thing that is remaining now is to interpret question A, B, and C. So on A, the question says the inlet angles of the first and the second moving row. So we need the inlet angle of the first and the second moving row of blades. So we can start by inlet. So we can start by inlet of moving row. This is, we are dealing with the first stage. So we got our angle as 30 degrees. So this is the one. The inlet angle of the first moving row is a 30. And then let's go to the inlet angle. Inlet moving row. We also want the inlet, but this one is for the second, which we got here as what? 43 degrees. So on our A, we are done. On number B, what do they say we must look for? On number B, they want us to calculate the power. So formula for power, we use on number B, but power equals to our mass times our U times our total wheel velocity. Our mass was given as what is the question saying? The power of the tube wheels per kilogram of steam per second. So in that case, per kilogram, which means that our mass is 1, our U, we said it was 3 centimeters. So we must take it back to meters per second. 3 times 50, which is 150. So we must use all our velocities in meters per second. And then let's go to our wheel velocity. To get our W total, we add wheel velocity 1 plus wheel velocity 2. So we add 22.5. That's our wheel velocity 1. Our wheel velocity 2, I measured it. It gave me 7 centimeters, which is from this point to this point. So plus 7 centimeters. I'm getting 29.5 centimeters. We must multiply by our scale, taking it back to meters per second. So we have 1 times 1/5 meters per second times, let me convert this. So it's 29.5 times 50, which I'm getting as 1475 meters per second. So 150 times 1475, I'm getting 221250 is power, so it's in watts. So if they want in kilowatts, you simply divide by 1,000, which I'm getting like 221.25 kilowatts. So that's how this question is supposed to be solved. But the most important thing now, which I need to emphasize, and you must not forget about this. Turbines are very simple. These are free marks in the exam as long as you understand the concept. Now, in power machines N6, our turbine only discharges at this point on the second stage. So this becomes our discharge angle, or we refer to it as our turbine angle. So this is the most critical angle, which you must also remember. Once you forget that one, is the end of the game. Secondly, our turbine is fixed on 2 positions. If it's a 2-stage like this one, all 2-stage turbines, they are fixed at 2 positions. The first fixed blade is the one which I said I will come back to it, as well as this one. Now, this becomes our fixed blade angle at inlet. So don't make a mistake on that part. Our fixed blade angle at inlet on a 2-stage turbine, it occurs here. This is where it transpires. And then the second fixed blade, it occurs at this point. This is our fixed blade inlet angle, but this one is not at inlet. It is now at what? At exit. So those are the most critical angles that you must remember. Our turbine discharges at this point. That's our discharge angle. That's our discharge angle. This is our discharge angle. Please take note of this. That's our discharge angle, or our turbine angle. And our fixed blade at inlet, it is only this one. That's our fixed blade at inlet. And then our alpha 2 here, that becomes our fixed blade at exit. Now, the other things which you need to remember when you are dealing with turbines is to understand the few terms like this one. When they say the gas is discharged axially. Now, when they say the gas is discharged axially, they are simply saying your turbine angle here is 90 degrees. So It simply means that your turbine or discharge angle is 90 degrees. The second important aspect which we must remember is when they say the blading is symmetrical. So we can talk about symmetrical blading. Symmetrical blading, it simply means that our beta inlet equals to our beta exit. In some cases, they can say there is symmetrical blading on both stages. Symmetrical blading, when we say the blading is symmetrical, we are simply saying this angle and this angle are identical. They are twins. If this angle is said to be, you found it to be 30 degrees, this one also becomes what? 30 degrees. If you are given this angle to be 25, this must also be 25. That is what is meant by symmetrical blading, or some books they might give the concept of saying the blading is equiangular. So that is one and the same thing. They are simply saying your beta inlet and your beta exit angles are equal. Remember that one. Don't forget that. Don't forget. And then, yeah, I think this is what is very important. This is what is very important. So I hope you managed to get a thing or two. Let's meet on the second session. Thank you.